So, let us draw the free body diagram of this so called leading shoe. So, now let us say if I draw this, so once again I am going to do a lumped analysis. So, let us say this is my leading shoe, let us identify all the forces that act on it, right. Let us say through the either the cam or the wheel cylinder I have an actuation force, right. So, Fa is nothing but the actuation force that acts on the brake shoe, right. So, now imagine a scenario where the brake shoe has rotated about its pivot, the friction lining has gone and contacted the inner surface of the brake drum. So, the brake shoe has been pushed against the brake drum. So, what is going to happen? The brake shoe is going to apply a normal load on the surface of the brake drum, and the brake drum is going to apply a reaction, right, on the brake shoe. Of course, the reaction force, reaction load is going to be normal to the surface of the entire brake shoe, but for the sake of simple analysis, simplicity, what we are going to do is that let us lump all those normal loads into one load, right. So, we are going to do a lumped analysis, right, and let us say the lumped normal load, I am saying that it acts somewhere here, and let us consider that to be some n subscript L. Okay, I hope it is clear what n subscript L is. The subscript L stands for leading shoe, n is the lumped normal load on the brake shoe, right. So, if once I have done this, I can now represent a lumped friction force on the brake shoe. As we know, the friction force is going to be perpendicular to the direction of the normal load. So, now if I draw the perpendicular line to the direction of the normal load, that is going to be this. So, this mu times NL, where now this mu is the friction lining coefficient or okay, we will say brake lining friction coefficient, let us call it that way, brake lining friction coefficient is the brake force that acts on the shoe. Now, should this be pointing upward or downward, this mu NL? So, let us reason it out by looking at this figure, right. So, now we see that the drum is rotating counterclockwise. So, let us say just to understand what is going on, I am at this point, right. So, now on the drum the braking process will generate a torque-wise clockwise torque, right. So, essentially since the brake drum is rotating counterclockwise, we are going to apply a clockwise torque on the drum. So, if a clockwise torque is applied on the drum, the deceleration torque, if you lump the tangential force at this point, you will immediately see that at this point the friction force on the drum is going to be upwards, right. Only then you will get a clockwise deceleration torque. Do you agree? So, that is the direction of the lumped friction force at that point on the drum. Now, what would the reaction be on the shoe? It will be downwards, right. So, this mu NL would consequently be pointing downwards, correct. So, in addition to this, let us say we have the reaction forces, let us say we label them as Rx, Ry. Let us say I am drawing it as a dashed line because we are going to neglect that effect. Let us say this is MLG, right, and another force due to the spring, let us say F spring, right, the restoring force from the spring, but we will neglect these effects, okay. So, now what we are going to do is that let me draw some dimensions. So, let us say we call this height, the distance between the pivot and the place where the actuation force is applied is some h, the place where we are lumping the normal load and the pivot to be some, let us say B, and the place from the pivot and in this direction to where the lump friction force is acting to be some A distance. Okay, so these are the this is the free body diagram. Okay. Now please recall the scenario that we are looking at, right. So we essentially have applied the brake, this brake shoe has gone and contacted the brake drum, right, and the friction torque is being generated. So of course the brake shoe is going to vibrate a bit due to the motion and so on, but then like we can safely assume that like we can neglect the inertia I alpha when we compare to the other torques, because the motion to overcome the clearance has been completed, right. So we will make that assumption and then like we will write down the equation. So taking moments above the pivot. So pretty much we are going to deal with this as a statics problem, an equivalent quasi static problem, right. So that is what we are going to do. So taking moments above the pivot, assuming that the inertial term is negligible. Okay, what do we get? So if I take moment about the pivot, so one counterclockwise torque which I am going to get is FAH, then we are going to get mu NL times A, right. So that is due to the friction force, that is another counterclockwise torque, and then a clockwise torque is going to be NL times B, and this we take it to be 0, right. So there is we are neglecting the other terms. So we have got a very simple equation, and this is something which is very interesting. Why? Because if you look at these two terms, FAH is the torque due to the actuation force, mu NL times A is the torque due to the friction force. See, by and large we associate friction with a negative connotation, right, which essentially is working against a process, right. But in this case you can see that the torque due to the friction force is adding on or augmenting the torque due to the actuation force, right, which is something which is quite positive about this particular shoe in a drum brake. And even if you want to look at a overall associate this equation with what happens, so since the drum is rotating counterclockwise, you see that moment the leading shoe contacts the drum, it is going to be pulled in, right, due to friction. That is the physics behind it and the consequent physical action. So imagine that this drum essentially goes and contacts the the brake shoe goes and contacts the drum. Due to the rotation of the drum in the counterclockwise direction, the brake shoe is going to be even more pulled in. That is the physics behind this is due to this term, right, mu NL times A. So the torque due to the friction force augments that due to the actuation force. Okay. This is specific to the leading shoe in a drum brake. Okay, we will see shortly why it is called leading, right. So this is specific to a leading shoe in a drum brake, and this concept is or phenomena is what is called as self-energization. Okay. So this happens only in the leading shoe of a drum brake. Okay. So the so called within quotes self-energization, okay, is a very positive attribute of a drum brake. Okay, we will see how it helps us. Okay. So, once again to repeat, self-energization is a phenomenon or the concept of the torque due to the friction force aiding the torque due to the actuation force in brake application, and that happens in the leading shoe of a drum brake. So, if you process this equation, what do we get? We get NL, that is from the above equation, we get NL equals FAH divided by B minus mu A, right. So, that is the normal load. So, this implies that the friction force from the leading shoe is going to be equal to mu times NL, that is going to be mu FAH divided by B minus mu A. Okay. Now, there is something called as a brake factor. Brake factor of the leading shoe, let us define what that is. So, the term brake factor is the following. So, the brake factor of the leading shoe, which we are going to indicate as BF subscript L, is going to be nothing but the ratio of the output friction force to the input actuation force. So, this is like output by input. So, if we substitute mu NL, what is going to happen? FA is going to cancel off, right, and then we will essentially get mu H divided by B minus mu A. Okay, so that is what we are going to do. So, this is an important advantage, because you can observe that looking at the mathematical term, right. If you look at the denominator, you are going to get B minus mu A, right. So, what is going to happen is that for typical dimensions and typical brake friction coefficient, lining friction coefficient values, this B minus mu A is going to drive up this brake factor a lot, right. So, isn't it? The denominator is going to be made smaller, right, because we are subtracting mu A from B, and as a result the ratio is going to become larger. So, would a larger brake factor be desirable? Of course, yes, right, because brake factor, as we have seen, is essentially the friction force output to the actuation force input. So, if I have a larger brake factor for the same input, I get more braking force, right, or to obtain the same braking force I need to give a smaller actuation force, right. So, I have an advantage from that perspective. So, of course, this discussion would be completed once we do the same analysis for the trailing shoe, which we will do now, right. Then we will be able to appreciate what I mean by larger and smaller. See, when I say larger smaller, we need to compare it with something else, right. So, we are going to do that. So, let us draw the free body diagram of the trailing shoe now, okay, considering the same dimensions, okay, under a similar set of assumptions. So, this is my trailing shoe, and if you mark all the forces, FA is my actuation force. Once again, we lump all the normal loads and then call it as NT. Now, mu NT is going to be perpendicular, of course, to the normal load. Okay, the question is which will be the direction. So, now let us go and reason it out. So, now we are going to look at this point, right. When I stand at this point, right, if I want to generate a clockwise braking torque on the drum, the tangential force on the drum at that point should be downwards, right, for the rotation that we have considered, correct. So, what will be the corresponding reaction force on the shoe? It would be upwards, right. I hope everyone got the logic, correct. So, mu NT would now be pointing upwards, right. So, and then like we use the same approximations, let us say this is my MTG, and then this is some F spring, right, and let us say there are some there are reactions at the pivot, okay. So, and then let us use the same dimensions. So, this is going to be h, and this distance is what we call as b, and this distance was a. So, once again we assume the same scenario where the brake shoe has contacted, and then we are drawing this free body diagram. So, once again we take moments about the pivot, neglecting the initial term. So, what do we obtain? So, about the pivot, now let us say I have FAH, that is going to be a clockwise torque. You can put a negative sign, or you can now just take in this fashion, right. So, we say, let us say we put FAH as a clockwise torque, which is positive, then what are we going to get? We are going to get minus mu nt times A minus nt times B, right, equals 0. Now, we can immediately observe that the torque due to the friction force is no longer augmenting the torque due to the actuation force. So, this is also something which we can relate in practice by looking at this diagram. So, note that the drum is rotating counterclockwise, I am pushing this brake shoe against the drum. So, the drum is, due to its rotation and due to the friction, it is going to push the brake shoe away from the drum, right. So, that is what is reflected in this equation, okay. The friction force will create a tendency for the brake shoe to be pushed away from the drum, okay. So, that is what is happening here. So, there is no self-energization, right. So, consequently what is going to happen? We are going to have changes in the equations. So, but of course please note that we are doing a very first cut rudimentary analysis with a lot of assumptions. So, we need to take these expressions also from that sense, right. So, they may provide an initial first cut qualitative comparison, right. So, NT is going to be FAH divided by B plus mu A, right, okay. This implies that friction force from the trailing shoe is going to be equal to mu NT, which is going to be mu FAH divided by B plus mu A, and the brake factor of the trailing shoe is going to be equal to mu NT, okay, let us denote it by BF subscript T, that is going to be equal to mu NT divided by FA, which is going to be equal to mu H divided by B plus mu A. Okay, so that is the formula. All right. Okay. So, now we can compare, right, for the same values of A, B, H, mu. Now, I hope it is clear what I meant by larger and smaller, right. If you compare the expressions for the brake factor of the leading and the trailing shoe, which one would be larger? Obviously, the leading shoe, right. The reason being the presence of that B minus mu A term in the denominator. What is the physics behind the B minus mu A term in the denominator? Due to this concept of self-energization, right, because friction force is aiding the actuation force in terms of the torque generation, right. So, that is the difference. So, you can see that the leading shoe leads the trailing shoe in the brake force generation. So, one can see that the terms come about from that perspective. So, 2 points, the concept of self-energization happens in the leading shoe, not in the trailing shoe. Consequently, the output from the leading shoe for the same input force would be more. the brake force output would be more in the leading shoe than the trailing shoe, right. So, those are two important conclusions that we can draw. So, we can immediately observe that if I reverse the direction of motion, what I have labeled as leading shoe and trailing shoe, they will get swapped, see, with everything remaining the same, right. So, if I just change the direction of motion of the drum from counterclockwise to clockwise, what we are calling as leading shoe would change to trailing and vice versa. So, as an exercise I want you to draw the free body diagram and convince yourself, right. Okay. That is one thing. Suppose we want a 2 leading shoe drum brake. By the way, this is what is called as a leading trailing shoe drum brake, okay. Okay, that means that it has one leading shoe, one trailing shoe. Okay, this is what is called as a leading trailing shoe drum brake. Okay. So, now if I want a 2 leading shoe drum brake, what should I do? So, suppose just for the sake of discussion, if I want a 2 leading shoe drum brake, what will I do? I will just push this pivot to this point and have an actuation force at the bottom for this shoe. Then you will see that for this particular configuration, the schematic that we are considering, both shoes will become leading shoes, right, is it not? But however, what is the, of course the advantage is that we get more brake force output for the same input because the brake factors increase, right, and essentially from performance viewpoint it is good. But however, what is the trade off? We see that to generate an actuation force at the bottom, we need to have a similar actuation mechanism at the bottom, we need to duplicate it at the bottom, right. So, for example, in a hydraulic brake system we will encounter this component called wheel cylinder. So, if I want to generate this actuation force here, I need to put a similar wheel cylinder here and I need to put a fluid line which will actuate the particular brake shoe. So, the cost, complexity, everything goes up, you know, like, and the unit becomes complex in that regard, right. So, that is what is called as a 2 leading shoe brake. So, today in most applications we have what is called as a duo servo brake, okay. That is the most common configuration used in automotive drum brakes today. So, what is a duo servo brake? Duo servo brake is just a modification of this leading trailing shoe brake, okay. So, typically what happens is that, like in today most drum brakes, there is an adjustment mechanism which connects the 2 shoes. What is a self adjusting mechanism? If there is wear and tear of the brake shoe, it just adjusts the initial positions of the shoes themselves, so that like the travel of the shoes are not increased tremendously, right. So, that is the concept behind self adjustment. So, due to that what happens is that these pivots are no longer rigidly fixed, but then I am just exaggerating to just convey the concept, they can be moved in some slots, right. So, because we want to push the brake pads closer to the drum if the brake wear is more. So, when this happens and the 2 brake shoes are now connected through a link, which is the adjustment mechanism, in the duo servo brake what happens is that when the brake is applied, the drum brake anyway is pulled in, right, due to this self-energization. Now, the drum brake also tries to apply a force, this shoe, not the drum brake, the leading shoe is pulled into the drum brake, so due to self-energization, and when the leading shoe is pulled in, this pivot essentially travels a little bit in the slot and tries to apply a force through this link on the trailing shoe. So, the trailing shoe is pushed from the top, it is pushed from the bottom. So, imagine this, you know, like previously we are having the trailing shoe only pushed from the top and there was a tendency for it to come out due to the friction force, right, direction of the friction torque, right. Now, what we are doing, we are pushing the trailing shoe much more effectively against the drum from both ends, right, to some extent. Okay. So, that way we are improving the brake force output from the trailing shoe, right. So, that is the concept of a duo servo brake. So, for the same set of components, right, you get a higher brake force output from a duo servo brake when you compare it to this leading trailing shoe brake. So, if you look at the brake factor output, brake factor of leading trailing shoe will be the lowest, followed by duo servo brake, followed by the two leading shoe brake. Two leading shoe brake will give you highest output for the same design, same dimensions, everything remaining the same, right. So, that is the what is say concept of all these brakes. So, finally, to just conclude, so the brake factor of the drum brake is going to be equal to the brake factor of the leading shoe plus the brake factor of the trailing shoe, which is going to be mu h divided by b minus mu a plus mu h divided by b plus mu a. Okay. So, this will be the total brake factor of the drum brake. Okay. So, I will stop here, and in the next lecture we will look at the disc brake, and then like we will compare the disc brake and the drum brake, and then like learn some critical attributes of them. Okay. Thank you.